So I've been making an analogy kind of between Gauss's law and between electric concepts of electrostatics and mechanics. I think I alluded to the fact, and maybe even pointed out that Gauss's law or uh, Coulomb's law is mathematically analogous to the universal law of gravity, and the definition of an electric field is analogous to Newton's second law. We made those observations. I think I might have also mentioned that I think I did when I derived Gauss's law. I told you that you could take a mass and basically replace the charge that we used to find the flux through the charge. If you find the flux through the mass, you'll come up with the there's a Gauss's law for gravity, and so I'm going to continue the analogy. I want to talk about, remind you of gravitational potential energy in a constant field, what that looks like. And I'm going to compare it to a charge in a capacitor plate. Now, I know we haven't talked about capacitance yet. I think we define it next. Well, actually, it might be either in this chapter or the next chapter. Let's see here. It might talk about capacitance at the end of this chapter. No, they separated. So some books put these two things together, potential and capacitance. This book separates into two separate chapters. But even though we'll talk about a capacitor plate more explicitly next chapter and talk about how it's created, and basically, for the purpose, we can introduce it here. And we can say that you can create a constant field inside a capacitor plate in the same way that we approximate a constant field, gravitational field close to the Earth. So you can create a constant electric field, that is. And remember, if you have for gravity, if we have here's the ground. And we have a mass here. When we raise it off the ground, we say that it has a certain amount of gravitational potential energy. And we can derive that amount of energy. And we do that by determining the amount of work that it took that the gravitational field did on the object, or the amount of work that I did on the object to lift it. There's a couple of ways you can think about it. Let's go with the easiest, most straightforward way, which is if I take a force and I apply a force to this object, I'm doing work on it, right? And we'll calculate that quickly, remind you how to do that. Well, when I do work on it, remember, work is energy and mechanical energy. And so if I've done work on this object, that energy must have come out of me to do it. Like I had to give up some work to do it. But remember, in general, energy is not created, there's conservation of energy. Now, there's different types of energy. In me, the energy was actually chemical energy, but it was converted to mechanical energy when I did work on the object. I will quantify this in a minute. But let's say that this is mass M, I pick it up through height h. Now, when you do work on something, even though work is a scalar, it can be positive or negative, depending on the object. So for me, energy came out of me, so it would be considered negative. But where did that energy go? It went into the object as work, and it was positive relative to the object. So when I pick this object up, I do positive work on it, but now that energy is in the object, and I can define how much it is by determining the change in the potential energy of the object. So yeah, right. So even though the energy left me, it wasn't destroyed. It went into the object as positive. So something had to change, either the kinetic energy of the object. In this case, it was, well, kinetic energy did change, but when I pick it up from the ground to height h and then it's just resting there, it has no kinetic energy anymore, but its potential energy is energy of position change relative to some the initial position where it was. And now what allowed me to do that was the fact that I did that in a gravitational field. So it's related to gravity, but we will show. So now basically when I do something like this, like for mechanics, I would do that a lot, but that's just representing that there's a constant gravitational field everywhere in this region of space. And that's just a shorthand way of noting that. Right. So as opposed to drawing this thing every time representing the constant G field pointing down, we just put a little G up in the corner and show the direction in which it's acting. But it's constant, and these field lines represent that. I should have made them solid, but I didn't want to. Same distance between the lines as you move anywhere in space, so it means that the field is constant. So this is what we're representing. And so because we have this object in this gravitational field, what we say is if I apply a force to this thing and pick it up, I'm just going to make it simple through a constant velocity as I pick it up so that I don't have to worry about the change in kinetic energy. There's a couple ways I can figure out how much potential energy it is, but I'm going to go with the definition of work, since that's what I described to you. Now, you might remember that work is equal to the integral of F dot ds, where S is the path length that it moves through. Now, in this case, so let's assume that I have an applied force on this object and I'm picking it up through height h. And while I'm doing that, I'm doing it in such a way that the force that I apply to it is a constant force. And it's equal and opposite to gravity. So while this thing moves up, if we do a quick force diagram on it, I can say that while the object moves up, so I, oh yeah, I just diagram it like that. So I'm applying force F, and the force down on the object is mg. If I pick it up at a constant velocity where the acceleration is 0 from the ground to height h, then obviously the first law applies, and I can show that my force then is equal to mg, right? Net force equals 0 because the first law applies. So F minus mg equals 0. So F applied equals mg. Now, we have to do a dot product between F and ds. ds basically, actually, I'm going to make it dy. I'm going to make it dy, just so it's a bit clear. ds is kind of the general formula that we used back in mechanics. But since I'm moving along the y direction, I'm going to just make it dy. Now, dy is just a differential path length. So dy has the direction of y, and it's just like splitting this path up into differential lengths. And you're doing the dot product between f and dy at every point. So dy is actually pointing in that direction, along the positive y direction. So here you're going to have the when you work out this integral, the work is going to be equal to F times dy times the cosine of the angle between F and dy. Well, if I'm picking it up, F is up and dy is up, so the angle between them is 0 degrees. Sorry. So angle of make theta 0, and that goes to 1. So what I'm doing is working out the integral of, I guess I didn't really have to do it as an integral. It could have been a constant force, but still, it's not much different than this working out. So F is mg. So I have the integral of mg times dy, where y goes from 0 to, a specific position, say h in this case. Now mg is a constant, so it comes out of the integral. So I have basically the work that I do on this object, if I pick it up at a constant speed, is mg times the integral of dy from 0 to h. And so basically, that's so the work that I do, if I pick it up that high, the work is going to be equal to mgh. Now, we do the units of mgh and we realize that it has units of energy. So what I realize is that the amount of work that I do on this object to pick it up through height h is equal to essentially the change in potential energy of the object. Because remember, this h is a delta y, right? Because delta y goes from 0 to h. So in general, we could say that the work done in a gravitational field, on a system like this is equal to mg delta y. Okay. And so that's when we then go ahead and define that quantity as gravitational potential energy. We say UG is defined as mg basically y. So then delta U is equal to mg delta y. Now, it's interesting because we're associating this energy with gravity. Now, I did positive work on the object as I picked it up, but gravity does negative work, right? Gravity is actually pointing down. And as it goes up, the angle between them is 180 degrees because dy was still up. So if I were to do this a separate problem where I calculate the amount of work that gravity does on the object, it would be equal to, it would be equal to, one way to think about it is that, let's think about it this way. If I now drop the object, right? If I drop the object, then gravity, how much work does gravity do on the object? Well, gravity is pointing down, and basically, even though in that case, actually, dy is still pointing up. So as gravity points, basically it's falling through a negative distance. That can manifest a couple of ways. You have to be careful about how you do that. But if you take the absolute value, you can just switch the limits around. And so it goes from h to 0. So the negative sign could come out in that regard, I guess. But the point is that either way, gravity does negative work on the object as an applied force does positive work. So what we can show is that since we define potential energy as mg delta h, what is the relationship between work done on the object as it moves through height h and potential energy? You got to be careful because there's a negative sign. It's defined as a negative sign, the relationship between these two things. You can kind of see it here. Like as I pick it up, I'm doing positive work. Gravity is simultaneously doing negative work on the object. So we can say that work is equal to the negative of the change in potential energy, and we define that as that's a general relationship actually for any kind of conservative force, which we haven't defined yet. But In this case, gravity is a conservative force, so that general equation applies. And when we put in the function for gravitational potential energy, then we would put in mgy for the u here. And I like to put a little subscript there because there's other kinds of potential energy, one of which we're about to look at right now. So all of that is a bit of a review that we have gravitational potential energy. And of course, when we look at Newton's second law, the relationship between force and potential energy is that F is equal to mg, or the weight is equal to mg. So the gravitational field, G, one way to think about it is that it's equal to, the magnitude is equal to work, which is a force. You can put a vector in there. Not work, but weight. So I'm just going to put Fg so it's not confused with work. So Fg, the force of gravity on an object, which is its work, is divided by the mass of the object, is equal to the acceleration. Now, in this case, we think of the acceleration as a kinematic quantity when we defined it before, something associated with the object. But I want you to shift your perspective now and think about gravitation as a field that's in the area close to the Earth. And that's another qualitative way why you can justify it doesn't matter what the mass is in that area, it's going to have the same acceleration, because the acceleration is a quantity associated with the region of space as opposed to something specific to the object. Again, it's just a different perspective of thinking about what acceleration is. As opposed to being a kinematic quantity, you can think of it as a conservative field in the region. And so even if it's a feather or a whatever it is, it's in that region of space, all those, it's the acceleration has to be the same, not because of the object necessarily, but because the region of space is defined in that way. Now, from Newton's second law, we've already shown that the reason you can think about it explicit to an object, even though the object has a different mass, is because that acceleration is a ratio of the weight of the object to the mass. It just turns out that ratio is a constant, but the weight is coming from G, right? If there was no G in that area, it wouldn't have a weight. It'd be weightless, or maybe unless some other forces are acting on it. So I think it is legitimate to think about the field as a property of the space, and anything that enters that space has to take on that property. It's just a different way of thinking about it. But the thing is, it's so interesting is that when we now look at a capacitor plate, I'm going to make an analogy of everything that I did here. But for some reason, we never think of the electric field as a property specific to an object. We always think of it because that's the way we present it. But what I'm just trying to show you is that we could have presented gravity in the same way. We just don't for some reason. Probably because I don't know why. I don't know the historical reference there, but I guess a point I'm making is that from the perspective of field, gravity and the acceleration due to gravity, and the acceleration due to gravity and the electric field are analogous quantities. All right. So this is gravity. I'm going to say acceleration. Or I'll say gravitational field because I want to focus on that terminology. Now, you should already know what a conservative force is. And that's something that we talked about last semester as well. I'm going to remind you of that definition here after I do this. So again, just to give you a heads up, my entire presentation of this chapter is very different from this chapter. It's all the same material, but just kind of organized and described in the same way. And I think I'm using different analogies to talk about electric potential than what they're using in the book. So again, you can go ahead and read the book. Always it's your book. It's the assigned book, and it just gives you a slightly different perspective. So it should be a little bit more comprehensive. But there are many books that kind of present it in the way that I'm doing it here. Okay, now let's look at an electrostatic field or electric field. So I'm going to set up a constant field with a capacitor plate, and I'm going to, just so we can be as close as possible to the analogy, I'm going to use a positive charge. Yeah. So now we'll talk about how to create a capacitor plate, a charged capacitor plate, next chapter, like I said. But for now, let's just say that we have this thing connected to a battery. We have electrodes here. I guess we have to have the circuit complete. So over here, we'll put a switch. So my switch will look something like this. And then we'll come here. Switch. So when I close this switch, it'll complete the circuit and the capacitor plate will charge up. Now this is positive and this is negative for my battery, and this is a symbol for a battery. I know we haven't talked about that yet. Battery. It's just like a little DC battery, like a little 9-volt battery or something you could buy. You can put in a little circuit here. And this is how you construct something like this in the lab. Let me make this better. Okay. So if I charge this capacitor plate, I'm gonna create a situation where the top plate is positive. Now we actually talked about these are metal plates, right? So we know that charge resides on the surface. We talked about that last chapter. I have positive. Now essentially, what does that mean? It means that basically I've taken away negative charges and exposed the positive charges on the thing, and I've deposited excess negative charges on the bottom plate. So that's how you charge. Again, we'll go through this very explicitly next chapter about what's actually happening with the charge and how it's moving. Right now, let's just say that we charged it, and this is what it looks like. So now we have positive and negative charges on the plate. So obviously, there's going to be field lines, right? Fields point from positive. We learned that also last chapter. So there's going to be an electric field in this region that looks something like this. The field lines will, they originate on positive charges, terminate on negative charges. So you're going to have a constant field set up in between those plates. And this field we can represent as E, the electric field. That's a symbol for it. So now if you look at these two pictures, you begin to see an analogy between the electric field and the gravitational field G. Again, that's what I'm trying to say. You can think of this G now as a very different kind of, conceptually, it's the same quantity, but you're looking at it from a completely different point of view. So I'm just going to go through and do the exact analogy of what I just did. I had now a couple other details about this I didn't go through because I'm assuming it's review, right? Whenever there is the mass is on the ground here at y = 0, we define that as the zero potential point. And it kind of comes out of the mathematics here. We set it up that way by placing my origin here. But I could have placed my, remember this origin, it doesn't know where you place origin. You could have put it anywhere. You could have put it down in a hole in the ground, put it up a skyscraper on the, on the top of a building. And when you do that, essentially what you're doing is redefining where you're calling zero potential point. So if it's on the roof of a building, it has negative gravitational potential energy when it's below that, right? Positive above. So all of that would be discussed last semester. Well, that still applies here. I can put my origin on the positive plate, in which the thing has negative potential energy falls down. But just for the purpose of illustration, because I like to make an analogy between capacitor and the gravitational field close to the Earth, I'm going to place my origin on the negative plate. That's the place where if I had a positive charge, so yeah, let's say I have a positive charge, and I place it here, the object doesn't want to move. Just like if I take a mass and I put it on the ground, the object is not going to move unless an external force comes along and does so. So to set up the really nice analogy, I'm going to pretend like it's kind of the same thing where I can, a positive charge in a electric, and this capacitor is very analogous to a mass in this gravitational field. So I'm going to set this up so that my y-axis is vertical and my x-axis is along the negative plate of the capacitor. And I get those confused, cathode, anode. I think the cathode is the negative and the anode is the positive, but whatever, I'll just say positive, negative. So yeah, cool. Now, same thing. If I come along here and I pick this charge up so that it is, at a distance h in my, let's call it d. I pick it up to a distance d along my axis. So I close, let's go ahead and say we actually closed the switch a while back. So yeah, I've got my axis here and call this height h. Now I'm going to pick my charge up so that it's here now. Well, I'll do the same thing. The electric field can do work on the object, or I can do work on the object. Both can do work. But let's say that I'm doing it. And I'm doing the same thing. I'm going to pick my charge up at a constant velocity. I can go through and show that my force must be equal and opposite to the, well, yeah, that's another point. That's another issue here. Let's say I'm not going to do the work. Let's say that actually, that's a good point. It's a very good point. When I do that, I'm working against two things. I'm actually working against gravity as well as the electrostatic force of attraction between the positive and the negative plates. I think we showed, we did show with Coulomb's law. We showed that. Go back and look at it. It's like second or third week. That the electrostatic force was it 10,000 times stronger than gravity? And we did by calculating the gravitational force on a elementary unit of charge, like a proton or electron. And we showed that that's the case, that it's going to be 10, I think it's either 10 or 100, I think it's 10,000 times. So basically, we can say that gravity, the weight is negligible here. So we can only I only need to worry about the electrostatic force. So we'll say gravitational force negligible in this situation. Gravitational force, weight, basically, is negligible. So that when I pick this object up, I'm just working, my applied force, F, is just working against the electrostatic force that I'm going to call Fe. So, yeah. Now, we already showed that the electrostatic force, we defined that a week ago or so, 2 weeks, that I'll keep the numbering going here, that the electrostatic force Fe is equal to the magnitude of the charge Q times E. Actually, we did the opposite. We said that E was defined as, that was the definition. E, the electric field, an external electric field of a charge, not the field of the charge now, but the external field that's, forcing, applying a force to a charge. It's equal to F, the electrostatic force, the Coulomb force, divided by the magnitude of the charge. That was the definition. So that means that F must be equal to, Fe must be equal to Q times E. And that's what I'm trying to show you. If you compare that to like this equation here, they're very much, they're similar. A gravitational force is equal to a constant associated with the object, in this case mass, times the field. Here, a Coulomb force is equal to a constant associated with the object, the charge, times an external field. So very much analogous. Now, if I'm picking this thing up again at a constant acceleration, so that, well, if I apply the first law, what I show is that my applied force, and just so I don't confuse, I'm going to call this APP, so for F applied. My applied force is going to be equal and opposite to the electrostatic force between the objects. All right, so I can say that, from the first law, we'll just jump to it. F applied equals Fe. Okay, well, now if you go through and take Fe and apply, so F applied, and determine the amount of work that I did on the object as I picked it up, very much the same. We'll go through it. So work is equal to the integral of F applied dot dy. No, it's getting pretty messy in there. I wanted to kind of finish it up here. Actually, I mean, just because I'm running out of space, I want to let you finish it up. But it's basically the same couple steps I had here, right? Like if you do the dot product, Fe is up, dy is up, the angle between them is zero, so you get cosine of 1. Fe is equal to Q times E, but Q and E are constant, so they come out of the integral. So whereas here I had the integral of from 0 to h of mg dy, here I guess I could write it in. I'm going to have the integral of, I'll go ahead and take it out, Q times E times the integral of dy. So that just integrates to, and I said I was going to make it d because people normally do that. And it just has a good ring to it because for the result that we get. In the same way that MGH is a kind of a nice way that, because we could have called this height anything. We could have called it X, but people normally make it H, so that in high school, when you're presented with gravitational potential energy, people say MGH, and it's just has a nice ring to it. And it's kind of, you say MGH, everybody knows you're talking about gravitational potential energy. Well, there's kind of something like that similar to electrostatics, that for whatever reason, people use this distance d in this kind of problem, so that when you get the final answer, the answer is QED. Now, QED also means something else in Latin, but it has a nice ring for it for a couple of reasons. When you kind of get the answer to a solution, QED. But here we're using it as QED, the electrical potential energy of a charge in a constant electric field. So here we'll say that it goes from 0 to d, the distance d. So in the end, you're going to get that the work equals, and I'm completely out of space here. I'm going to go ahead and erase this thing. It's kind of in the way here, but in the end, we can say that the work is equal to Q, the magnitude of the charge, E, the magnitude of the field, and D, the distance that have gone, in that field. I've raised the object from 0 up to, that position, 3D. So I know I kind of went through the definition of how we're making this analogy between energy and work, but same thing, and because it's review for mechanics, same thing over here. We say, oh, well, if you look at the units of this thing, QED, it turns out to be units of joules. So you realize that that's energy, right? And so the same analogy, the argument I can make, the work that I did on the object by picking it up, that work went out of me and went into the object as potential energy. So we've already defined in general that there's a relationship between potential energy and the change in potential energy and work. So if I define over here, if I define the electrical potential energy as QED, then I can say that the relationship between the work and the gravitational potential energy is defined by the general equation for potential energy, or general definition of potential energy, which is equation 12 here. So we define UE as QED, and ultimately then we can say that um, that the work is equal to the negative of the change in electrical potential energy as well. Yeah, yeah. So if you look at equations 19 through 21, as well as equations 8, 10, and 12, we have these wonderful analogies between uh, a gravitational field and an electrostatic field, and the work that can be accomplished within those fields by changing an object's position, and the potential energy, so the change in potential energy associated with that work. So that's how I like to start qualitatively presenting the idea of electrostatic potential energy. Okay? That's the basis. That's the fundamental foundation, because I know you can understand that, because basically you already do, right? We already do for mechanics. And again, my whole presentation of electrostatics in the first few chapters is just making analogies between uh, what we've discussed in mechanics for here, because it's just, you already know the relationships. So it's just, or have an intuition for those relationships. So that's a really great basis for understanding the concepts of electrostatics. Now, again, in your chapter, in that first section, they're really doing the same thing, but they're doing it from a kind of a different point of view from what I'm doing here. So it might not kind of look the same initially, but in the end, it is. It's ultimately leads to the same results. But I like this better. I like they're kind of coming from the point of view of force and Newton's laws. I'm coming from the point of view of potential energy. So that's why it looks a little different. Um, but ultimately, like, again, that's why, again, perspective is one of the themes of the course, because it's really just a different perspective, right? And speaking of which, I didn't specifically point, I guess I did it here, but yeah, I guess we could actually box this in as well. Whereas gravitational force, is mg, electrostatic force is QE, right? Those are also analogous in a sense. We don't call electrostatic force a weight or anything, but in gravity we call it that. But basically, it's just the mass times the acceleration field of gravity, the gravitational acceleration field, and for electrostatics, it's charge times the electrostatic field. Okay. All right. From there, I like to I just had a brain fart, as they say. Oh yeah, I wanted to review the idea of a conservative field. What that means? Well, oftentimes, we actually presented it from the point of view of conservative force. That's actually what we said last semester. Last semester, we discussed the concept of a conservative force. Now, a conservative force had three properties. It is the work done by a conservative force is path independent, meaning in these analogies, I pick the object straight up, right? The shortest path between 2 points. But I didn't have to necessarily take that route. I did that route because it was easiest to illustrate to work out the integral for the straight line. But I could have taken various paths, infinite number of paths. Could have gone in a semicircle in opposite directions. I could have taken a squiggly path, gone even above H, and then come back down to H. I could have done any sort of thing, all kinds of things. In the end, because the change in potential energy was only dependent upon the difference of the positions from position 1, which is the ground, to position 2, which was H in the case of the mass, D in the case of my charge, nothing else was in that formula about the path, just the difference between the final and initial position, which means that what we say in physics is that the work done is path independent. And it's really simple because if you were to, for a straight line, the path is either parallel or anti-parallel. So when you look at the cosine of theta, you either get 1 or -1 that comes out. And it turns out that the cosine, but if you actually were to take if you were to take a path ds that's at some angle to the field, then what you would find is you would actually have two components of work. One would be your force times the cosine of theta, which is what we're doing here, the definition of work. But the other would be your force times the sine of theta. And we showed last semester that a property of the force is that only the components of a force in the direction of motion actually do work. And in terms of this situation, it turns out that the sine of, basically the sine of the angle, it's not that it's zero, it's that it adds up to zero. Because if I deviate from one, if I go along a horizontal, where kind of hard to illustrate it here, but basically just all the components perpendicular to the direction of the force, they would end up adding up to zero. So basically, again, we talked about that in mechanics, why that is. And so only whenever you're doing work on something, only the component of the force along the same direction, which means either parallel or anti-parallel. If it's parallel, it's positive work is being done. Anti-parallel, negative work, energy coming out of the system is being done, or transferred to transformed into some other kind of energy, like potential to kinetic as an object falls. At any rate, only the parallel components or anti-parallel components do work. So, or do a net amount of work. So the object is path independent. Now, in a similar fashion, if I were to then calculate work on the object as I'm lowering the object, so I picked it up, I did positive work, mgh, but if I lower it, basically, I guess you could say that mg and h are in the same direction still, but now I'm going from final to initial, My final is 0 and my initial is H. So when I do that delta Y thing, there's a negative sign that comes out. So in that case, I get negative work. I'm doing negative work when I lower it. And you would see that again, if I'm moving at a constant speed, then the amount of work that I do is negative mgh. So if I looked at a total trip starting at the ground, going up, and then coming back down, the total amount of work that I would have done through one round trip will be 0. And that then becomes a property of a conservative force and what we say is that the total amount of work done on an object through one round trip within a conservative field is always 0. Now, technically, they kind of focus on the work done by the field itself, but in this analogy, because I picked it at a constant velocity, the work I'm doing is always going to be equal to the work done by the field. So again, we can just say that. So yeah, and the final property of a conservative force is the one that I just illustrated here for both of these, that we were able to define a potential energy function associated with the force, with the conservative force. In the case of mg, we put that force into this work function, I call it, and then find the amount of work done. It's going to be mgh. So the conservative force is now associated with a potential energy function, a gravitational potential energy function. And same thing with the electrostatic force. So the three properties of a conservative force are, and this is how you know that you're dealing, well, this is how you quantify that you're dealing with a conservative force. I got another quick and dirty way of illustrating how you know you're dealing with conservative force in a minute, but I just wanted to review the quantifiable ways that we define a conservative force. So conservative force, the properties, path independent, work is path independent. Um, Zero work through, use my shorthand spelling of through, one round trip. And conservative forces have potential energy functions. Yeah, I guess I just could use the potential energy function. So we can define some sort of potential energy function. And yeah, now one quick and dirty way of determining whether a force is going to be conservative or not In the case of both gravitation or gravity and electrostatics, the source of the field in the case of gravity, the accumulation of matter. In the case of electrostatics, a proton or an electron, they do not have to touch the object that they're forcing upon in order to cause a force. In other words, they are not contact forces. That is a key signature, an obvious signature to be able to quickly determine if it's a conservative force. Now, if those things are true, it definitely will be a conservative force. If they're not true, doesn't necessarily mean that it won't be a conservative force. And there's one exceptional example that I'll talk about in a minute. But if there's some system that is being forced upon by some force that is basically has a field, in other words, then it's going to be conservative compared to something like friction and drag. Oh, and friction and drag. Well, we know like drag, those are contact forces just by the name set up. And so, when friction is doing work on something, you rub your hands together, you get the heat. So you can only get the friction if your hands are in contact. There's nothing in the region around my hand where friction can cause work to be done on my hand without something else touching it. It has to be contact. And in fact, if you go through and look at each one of these points for a contact force like friction or drag, each one of them will be violated. Obviously, with friction, if I'm, calculating the amount of work done by friction, the path matters, right? Because, the longer the path, the more friction, I apply. So if I go between 2 points, A and B, well, if I go along a straight path, that's going to be a certain amount of friction. But if I go along some varied path, then I've got more friction. I'll generate more heat because I'm in contact for a longer time period. So clearly, the first path is not is violated, but also it's obvious that the second one, or the second point is violated as well, because you don't get negative friction by going in different directions. If I go up, I have mu times n or whatever the normal for. If I come down, there's mu times n. So the friction, the amount of work done, increases because my frictional force doesn't change. Yeah, yeah, that's a great example, right? Like whatever the work done by friction is going to be twice as much work going up as coming down as opposed to canceling out to zero. And for the same reason, this is it's better to see it in a circle. So if I start at A and I move around in a circle, when I get back here, the amount of friction that it's not going to be zero. It's going to be basically, the work done is going to be the friction of force times the circumference, basically. It's not going to be zero. So you do get zero work doing one round trip when you have a contact force like friction. And this is a little bit more subtle, but with the potential energy function, when you actually calculate the amount of work, basically you get constants. You don't get something in the case of it's a little bit harder to kind of see that, but in the case of friction, again, if I were to calculate the work done by friction going around in the circle, everything that I get will be a constant associated with the circle, even the radius. Like you're going to get the work done in the context of the circumference, 2 pi r, but those things are going to be constants associated with that circle. We don't think of when we do the work done in gravitational field as mgh. Yeah, mgh is a value, but that's a specific value just for that height that I went to. In general, it's actually a variable. You get mg delta y or mgy, and the variable has a value depending on where you stop. So what we say is that when we calculate the work done by gravity and a gravitational field, or the same thing with a charge, that potential the work is dependent upon a variable. It's dependent upon the position at which you stop, and that's not a constant. And that's why you can call it a function. You can then say, well, define it as a potential energy function, because it's something that varies depending upon the height where you are. Once you establish a system, which is a circle, and you're calculating the work around that circle. Now, I know you can say that you can vary, the circle, which you can, but that's kind of like saying, well, if I go to the moon, and I go through the same height, my potential energy is different. I've changed my system, but within that system, the energy is varying based on the system that you set up, the specific system where you're calculating the potential energy. So once you choose a particular specific system, the Earth, the Moon, some other planet, and then calculate, you're still getting a variable energy based on how high you are from your zero potential energy point. So you're not getting a constant, it's a variable, it's a function, so it can be defined as a function. In this case, the system would be the specific circle that you're taking. So once you define that specific system and you calculate the energy around that circle with the specific radius, you get a constant. You do not get a function. And what that is showing you is that, and again, when you get back to zero, you don't have any potential, like you go around in a circle or whatever the distance, and you then stop moving or whatever, there's no potential energy. Like you haven't put, friction does not put energy into the system. So it doesn't create a system where there could be potentially a change in energy based on position. All friction is doing is doing work on the system, and whatever mechanical energy that's in that system, it's actually taking it out of the system. It's not putting energy into the system. So there's no function to define the potential energy that it has once the friction does work on the object, in the same way that we showed that that's the case for gravity and electrostatics when you're moving an object around. So for all those different reasons, the amount of work done by friction cannot be defined as a function, which means there's no energy of position that it has after being worked on, the object has after being worked on by friction. And in fact, because there's a negative sign associated with that work, what you realize is that in all these other cases, when you truly have a conservative force and you do work on it, you could potentially put energy into the system by changing its position in a certain way. Whereas with friction, that will never be the case. The work that's done by friction on that system is always converting mechanical energy to heat and taking that by thereby taking that mechanical energy out of the system. And in fact, all contact forces that I can think of do that same thing. Now they have different functional forms, but in the other two are going to be drag and a viscous force. And drag is a kind of viscous force, actually, but whatever. If we want to separate them like that, drag, friction, viscous force, they all convert mechanical energy to heat and take that energy out of the system. So there's no function that you can define. Basically, contact forces do not have potential energy functions. And so thereby they can be considered non-conservative forces. So for all those reasons, contact forces are non-conservative because they violate all these. But the easiest way is to understand is, do I have to touch this object, to do work on it? With drag, friction, and viscous force, yes. In the case of friction, it's the contact of the surfaces. In the case of drag, it's the molecules of the air. In the case of, viscous force, it's the molecules of the liquid that's, making contact with the surface of the object as the object moves through that fluid. Whew. So that's a review of contact forces. Now, if you notice, what I was saying when I started this conversation was conservative fields. Well, now that we've established our memory of what a conservative force is, what we can simply say is that conservative, and you might say, well, what comes first, the chicken or the egg? What comes first, the field or the force? I would have to, obviously, the field is there first, right? So I would say that conservative forces are associated with conservative fields. And I can prove that very simply. Which comes first, the chicken or the egg? Okay, now that we're thinking about gravity as a field, and I've erased the picture, but everywhere close to the surface of the Earth, there's a field, and its value is 9.81 meters per second squared. It's an acceleration field. Now, I know that feels odd. You can say that, how can you say that acceleration exists if there's no object being accelerated? Because I just told you earlier, it's how we started this lecture. Thinking about the acceleration as some sort of property associated with an object is one limited perspective of thinking about acceleration. You can think of it as a field which is independent of any object, and it just exists in the air. I know it's weird to think about it that way, but you have to convert to thinking about the concept of a field. This is why I say that, Michael Faraday is given credit for that definition of field. And he did it by applying it to electrostatics, that E is equal to F over Q. But this is why I feel that Newton probably had already done that 100 years before. Because when you look at, you cannot convince me, and I have no proof, but you cannot convince me that this dude was as brilliant as he was, genius as he was, didn't actually think about this, did not actually think about the fact that you could define gravity, acceleration due to gravity, independent of some object that's experiencing, because we certainly think about that in terms of force. What we say is there's a force field around the Earth. Well, it's basically the same thing. The force, and that's what he's saying in the second law, right? That's what this equation is saying. Yeah, F equals mg, the force of gravity, is equal to mg. But, and then we draw the Earth, right? Here's the Earth, whatever, I don't know, Earth. But then we say that the gravitational force field, and we kind of use that term, force is not really a field. It's kind of a misnomer. The field is the G associated with it. But in science fiction movies, people say, oh, force field. Well, the force doesn't have a field. It's just, force is specific to an object. But it's the field around the thing that, it's causing the force that's actually setting up that the field is actually the G field, which is not so much associated with the object, it's not associated with the object that's being forced upon. It's really associated with the object that's doing the forcing. And it's all implicit in this definition here, because once you choose an object and you put it, so I take an object and I put it at this point, say this pen. Well, now it has a force on it at that point. The force is the force of gravity. If I take the pen away from that point, is there a force there? No. But is there a field there? Yes. And if I take another object and put it in that same position, now there is a force there, but it's the force associated with that object because the mass of the object is different. So truly, the force is associated with the object, but the G, the thing that's causing it to have a force, it's there in that region, whether that object is there or not. And no matter what object I place there, even though the force changes at that point because the mass is changing and because now I have an object at that point, the G is still at that point and it's not changing. So truly, you can think of G as in the area, in the region of the space. In fact, you can think about the force and not even know that it's coming from the Earth. Like maybe you're so far away, I don't know, or maybe I'm on a mask or something, I don't know. But you can detect the field in that region, by measuring whether there's a force or not, and then doing several objects and realizing that, this field is a constant multiple of whatever the mass is. So the mass is specific, and we already know that mass is inherent to the object for other reasons. We talked about that during the first law of inertia. But the G field is associated with the space. Now, you can't convince me that Isaac Newton didn't think about that. I'm sure that he did. I'm sure that he understood the concept of a field and defined it for himself. But he didn't publish it. He didn't say anything to anybody about it. So Faraday gets the credit for, and I don't want to take anything away from Faraday, that he discovered it independently. But you will not convince me that Isaac Newton didn't know about a field. He did. I'm sure he did. But in the same way, he invented calculus and didn't tell anybody about it until someone else did it. I guess he just chose not to, did so many other things. Like he didn't do that, whatever. So we'll give it to Faraday. um, yeah. But anyway, so I'm just trying to say that it was already there. It was already inherent in Newton's second law definition, the idea and the concept of a field. And in that case, it would be conservative because you don't really need an object touching something to force it. And that's, again, I don't want to be redundant, but clearly that's the case for electrostatics and for gravitation. Right. So what comes first, the chicken or the egg? Well, I don't know about that question, but if you ask me what comes first, the conservative field or the conservative force, I would have to tell you that not only does the conservative field come first, um, it actually creates the environment in which the conservative force can be uh, realized on an object. Mm, mm, mm. Looks like it's break time. That's a good stopping point. So I guess conservative forces come from conservative fields. So when I'm using the term conservative field, that's really what I'm talking about. So now again, we don't really have definitions for that, but we define conservative force, and now I can just take that one step further and say that a conservative field is one in which the force associated with that field is conservative, is itself conservative. We'll write that. So, uh, the last thing that I will say then is that there was one force that was conservative that violates this. It doesn't violate it, but it's just, and that was last semester. You might remember there were two conservative forces that you discussed last semester. One was gravity, force of gravity. The other was a spring force, Kx. An ideal spring also has is considered a conservative force, but it's ideal. Remember, kind of like frictionless surfaces don't exist, but whatever, we deal with them. A spring, when you attach a spring to something, technically it's actually contact, but what we're assuming is that one, the friction is so small that it's negligible, so we say it doesn't exist because the areas of contact of the spring and the object are so small compared to their surface area. The other thing that's conservative about it is that if it's an ideal spring has no mass. And because when it would move, actually there would be friction within the molecules of the thing and it would generate heat but if it doesn't have any mass, then that doesn't happen. So for those reasons, we kind of, the force of a spring is kind of like an honorary, like people get honorary degrees, from schools, but they don't actually, whatever. So I kind of think of the spring force as an honorary conservative force because the fact that we make it ideal is why it passes the criteria for a conservative force. Well, it passes two criteria. Well, actually, it passes the criteria because it also has a potential energy function as well. But it's just because it's ideal. It's an ideal kind of unique situation. So an ideal spring is also a. Now the thing is, it actually, because it's honorary, it has a potential energy function. We don't describe it as having a field. There's no field associated with the spring. And again, this is because it's an ideal spring doesn't exist. It's a mathematical construct that's not real. So, something's got to give somewhere. And so I guess what gives is that it doesn't have a field associated with it, even though, and that doesn't even make any sense really. But from a realistic point of view, but from a mathematical point, from a definitions point of view, whatever. I'm saying the same thing over again, but I hope you get the point. In fact, we might be able to define a field associated with a spring, but we just don't do that. So I'm kind of drawing a blank now. I think I need to take a break and get a bit of a bite. But the next thing that I want to do, the final thing, is to associate the field with the force. We have associated work with basically a field because we've done it to the potential energy. We've associated a force with work because that's the definition. But we haven't directly associated a field, a conservative field, with its force. What is the relationship between the two? And so we could use everything that we've done thus far to just couple one step or two, and we can have that. And so I'll do that one. That'll be the first thing I do when I come back. Is what is the direct relationship between a conservative force and its field? Okay, I'm gonna take a break right now. So we're back to this. So we had shown that that electric potential energy is equal to QED. QED and a capacitor plate. Yeah. So what I want to distinguish here, I guess, in order to show the relationship between I had said the E and F, the force and the conservative force and conservative field. Guess what we really have to do is well, we really need to, at this point, define what electrical potential is. Now, this is electrical potential energy. It has units of joules, it's energy. I'm going to put an emphasis on energy, the word. The thing is, electric potential, the concept of a potential is actually a new quantity. You're starting to get to be intermediate students now, and much of the quantities that we discuss are, I mean, there's still new things that you're discovering, but this happens to be a quantity that we could have actually talked about previously. Meaning, if I'm looking at using the analogy between energy and between mechanics and electrostatics, as I've been doing, the concept of a potential is actually something we could have talked about before, but for conventional reasons, we elect not to do so. But there is something called a potential is different than an energy. So gravitational potential energy or electrical potential energy is different from electric potential. In the same way that gravitational potential energy, MGH, is a different concept than gravitational potential. There is such thing as a gravitational potential, but we did not define it or even talk about it last semester. I'm not going to go back and do that now. I just want you to mention that it does exist. The analogy does not fail when it comes to electric potential. I will be a bit more explicit about some of the implications of electric potential uh, when we get to circuits. But for now, for now, I'm just going to qualitatively define what electric potential is, and then I'm going to relate it to electric potential energy. I guess the best way that I could describe this is that when we think about potential energy, we generally think about, in the case that I gave you, it was a specific object, and I pick that object up. But and so I define the total energy, potential energy of that object. But we definitely know that energy is associated with mass. If there were no mass, there would be no energy. In the case of gravitation. And here, let's just deal with this. And this is the total energy change, potential energy change, as I move that charge from the positive plate to some other region within the capacitor plate. It's the total potential energy, the total energy of position of the object. However, if I have several objects, and this is, you can also define it with respect to one object, but it kind of makes sense to talk about it more of a collection of objects. If I had several charges and I'm moving those charges within a electric field, maybe even groups of charges, um, and different numbers of particles within each group. It doesn't, if I want to compare, I guess sometimes it makes sense as opposed to looking collectively at the total amount of charge, total amount of charge. It makes more sense to talk about the charge, the amount of energy per unit. So in this case, the amount of energy per unit charge. So if we divide this equation by charge, that's what we get. This represents the total energy of one charge, but if I divide through, I'll number this equation one, by charge, what I get is that the potential energy divided by Q is equal to ED. This represents the energy per unit charge. So this represents the total energy, in this case, energy of position. And what we're talking about is of the system. In this case, the system, well, technically the system is the charge within the capacitor plate, but specifically just the charge itself. But as I said, we could have a different system, a collection of charges, whatever. And so when we define that by charge, we get, obviously we don't have units of energy anymore. We have basically units of energy divided by units of charge. So joules per coulomb. And we define this quantity as a potential, not a potential energy, just potential. So this is defined as electric potential, and we give it the symbol V, capital V, and it actually has its units are volts. We define those as the units. So a unit of a volt is a joule per coulomb, and we define the quantity that mathematically describes that as a electric potential. In short, a voltage. So the symbol is V. In fact, it makes sense to talk about delta V, really, to be honest with you. So really, the more general relationship here, as I showed you, let's just do it again, is that, because here, one of the positions was zero, but it's really, it's more sensible to talk about a change in potential energy as opposed to potential at a particular point. So a delta UE is equal to a QE delta Y. And so therefore I can define a potential, a change in potential, a change in electric potential as delta U is equal to, delta V is equal to delta U over Q. And that in this particular case, in general, this is the relationship. We don't have to put the ED there, but in that specific case, that would also be equal to ED. And so this becomes the definition of electric potential. Electric potential or voltage. So voltage and the term electric potential are synonyms. They're describing the same physical quantity. Electric potential has units of, you can see here, joules per coulomb. And so, if you want to say, what is it? Well, it's, as I said, it's the energy per unit charge of a system of charges within an external electric field. Again, as we said, with gravity, if there's no external field, there's no energy, right? The field has to be there. The E has to be there. And we can then speak collectively about the total amount of energy for a particular charge or particular system of charges, Or we can talk about the energy per unit charge, and that is what voltage is. So electric potential as units of volts. So a volt, named after the German physicist Volta. I'm not sure what his name is. And joules or coulomb, and symbols that becomes the symbol for volt is capital V because it's named after Volta as the proper name, so you capitalize it always. So as with joule, also capital, so as with coulomb, all capital letters because they're named after the physicists who, physicists named after physicists. Yeah. And so that's the general definition of potential of electric potential. And here, in fact, I'm putting, you know, honestly, we'll leave it as that, but honestly, it's a general relationship. So there's actually a gravitational potential. Again, we don't call it volts. You kind of think of it as electric potential always associated with electricity, but it isn't. It's a more general relationship that it's the it's the potential energy of a conservative field divided by basically some constant that's an inherent property of the object that has the energy and that is used to define the potential energy. In the case of gravity, again, it would be this. There is a gravitational potential, as it turns out, and it is actually defined the same way. It's uh, I'll just put like a V because that's the only symbol we have. Well, actually, I think they use phi. Gravitational potential G is equal to, and we'll put a change, is equal to the change in gravitational potential energy divided by the mass. Just, for your information. Now, we don't obviously call it volts. In fact, the name of it doesn't have any units. It's just joules per kilogram. But it exists. Okay, so yeah, but back to what we're doing here. Yeah, and so now that we have this relationship, we can actually we can actually use it now. We can actually use it to define the relationship between. Remember, that's where I was going. The relationship between the conservative field and the conservative force, and it comes out of we can start here to a couple ways we can get to it, but this is one way. So let's start with this general definition, and I guess we can do this. Well, there's a couple ways we can get to it. I think I'm going to go back. Since this is new, I'm not going to start that. I'm going to start from stuff that we already know. And what I had shown you earlier is that, we use work, the integral of F dot dy, but we also have the general definition of potential energy minus delta U. If two things are equal to a third, they're equal to one another. So one way of getting to this is to equate these two guys as well. So 4, 5, 6, 7, 8. So equating those two things, we have basically the integral of f dot dy equals minus delta u. Now, I can bring the minus sign over and I have, that minus the integral of f dot dy is equal to u final, so I just call it u minus u naught. Now, in most cases, we define u naught as 0. I think this is going to give me what I want. So, take that out. And I can say that the potential energy then is equal to f dot dy. Yeah. But now I can make that, and that's in general, but now I can make it specific to electrostatics. So I'll have u is equal to minus the integral of f dot dy, but the u is equal to the potential delta V divided by Q. So that, so times Q. So I can use this definition in here and I can say that U is equal to Q delta V. And actually, if I made the 1 0, the delta over, yeah, right. In fact, what I'm trying to do is apply this to the capacitor plate. So in that plate, we said F was equal to E times times Q. Yes. So for the capacitor plate, that became, and again, the angle is 0 along, like if the positive, if the charge is moving down, right, in the capacitor plate, because it would, like if I pick it up and let it go, then the electric field will cause it to move back toward the negative plate the way we had it. So or yeah, or even vice versa, the way so I guess there would be 3 equal signs in that case. The dot product would generate a negative sign, but then I'm going from H to 0. I'll final minus initial, so H to 0. So basically, this generates a minus sign. The minus and F is equal to Q times E. It's outside the integral dy from H to 0. And so yeah, that minus sign, so minus and minus will make this a plus. There's 3 minus signs. And then when I do the integral, I get another minus sign. So Q delta V is equal to negative Q E E, basically, oh, I said to D, not to H. QED. Sorry, I'm running out of space over there. I think you might actually see this in the book. I do this as an example. We get a very unique situation. I'm sorry that I erased the picture already and I could show you explicitly, but let me write this a little bit larger over here. So equation 13 becomes, in fact, let me work it out a little bit. Let's start back here. Take this out. It's a little bit larger so you can see it. So this u is equal to minus integral Fe dot dy. So let's do the problem where, so here was my capacitor plate here. So I had the charge there somewhere. And let's do a situation where we're going from, this is plus, this is minus, and this is a distance d in my axis where I had it set up. Let's look at the work done by the electric field as it accelerates this charge back down to the positive plate. So this is a distance d, is where we are right here, okay? So that integral, I'm going from d to 0. Now this minus sign, mind you, it's already there because it was in the formula for the general definition of potential energy. Now let's work out the integral. First, I have to do the dot product. Now F is pointing down, but dy, because I make my positive y-axis up, basically dy is pointing up. This is y and this is x. So as the angle between them is 180 degrees. So when I do that dot product, F dot dy is cosine 180 degrees, it kicks out another minus sign. So that's what I was kind of doing in my head over there. So so here we're going to have the electric potential energy is equal to minus the integral of F E dy times the cosine of 180 degrees. And again, we can make the note that mass raised to height d, and then let's go. It then accelerates down when you let it go. I'm not going to write that. I just used it to get it from my. So this kicks out another minus sign, -1. F is just, it's just the force on this thing in the electric field is, this electric field is E. So F is just, it's Q times E. So then this becomes the potential energy. And actually, I should still deal with the change because it's changing, right? So I guess I should put the U final back in. We don't have to make it 0. Again, it doesn't really make sense to talk about potential energy at a point. Let's just keep it delta U. Okay, so this is delta U, and over here we'll have delta UE. Delta U. Okay. Because we don't necessarily have to go all the way down to 0, right? We could have, what is the change in potential energy going from this point to some other point that's not non-zero? So we'll keep it like that. So that's going to be equal to, minus and minus is a plus. This is H or D to 0. So we have plus D to 0, actually. Yeah. D to 0 of Fe, but Fe is Q E dy. And you can remember that. Just put that here because Fe equals QE. And then those are constants that come out of the integral. So what we're integrating is delta U equals Q times E times the integral of dy from D to 0. So final minus initial is going to kick out another negative sign. So we have that delta U is equal to negative Q E D. Now that's cool. So that gives you the relationship between potential energy. We've already done that. But now that I have this definition, I can define a relationship between E, or between the voltage and the electric field. So if I do that, if I plug in 4 into 17, the definition of potential into 17, then I get this a very specific and unique relationship between potential, electric potential, and the electric field for a constant field. So 4 into 17 gives that 18. Um, so delta U then from 4, delta U is equal to Q times delta V, and putting 8, so I guess 18 really into, this is from 4 from the definition, and then 18 into 17 gives that Q times delta V is equal to minus Q. And that D, I mean, that's ED, but it's really delta Y, I guess you could say, delta Y. Let's just go back to the general. So the Q's go out, and you have that delta V, the change in voltage, electric potential, is equal to minus E delta Y. In terms of absolute value of the change in electric potential is equal to E delta Y, or, if you had values, it's ED. So delta V is equal to the field times the change times the displacement. Now it does have an integral form and a differential form, which is nice to know. The integral form of this situation is that delta, going back to equation 20, delta V is equal to the integral of E dot dy. That is to say, I could have plugged that in the beginning, this definition here, and just solved directly for the potential. Once I have that definition, I could have plugged into, I've erased it already. I guess it was here in the space, but delta V is equal to minus E dy. And in general, but for a constant field, so this is a general relationship where you have to integrate it. But for a constant field, when E is constant, because E might be dependent upon Y, it is for a point charge, and we'll see what happens when we do that. Get a different potential energy. But for a constant field, well, actually, we can just say that equation 21 applies whenever E is constant, so we can plug that in. So this is in general, and 21 is for a constant field. And I'll say that here. 21 is a unique, unique, that's right, relationship for constant E. And E is constant in a capacitor plate, as I showed you. In general, the relationship is going to be defined by this integral, which you have to work it out. and the potential, the electric field, if it's not constant, you have to work out the integral. So in general, equation 22 applies. Okay. Hmm. I probably misspoke earlier. I said we were going to get a direct relationship between the force and the field, but I guess there really is no direct relationship. Um, yeah, not really, unless you do a differential. I mean, yeah, I mean, we already have it. I mean, it's just the definition of, I guess I misspoke. I meant the direct relationship between the potential in the field, the energy in the field, and the energy and therefore the potential in the field. The direct relationship between the force in the field is just the definition of a field. Right, I said that earlier, so I misspoke. I was thinking potential and I said force. The direct relationship between the force and the field is just the definition of the electric field, just that. And for gravity, it's going to be the force of gravity divided by mass. So those are the direct relationships between the force and the field for, yeah, between the force and the conservative fields for the conservative fields that we're familiar with. And as I told you, there is no uh, the other conservative field that we work with, the spring force, doesn't have a field. Um, it has a potential energy, but we don't define it as having a field per se. So we don't have a relationship like that. Although I never thought about it, I guess you could define one. Guess it might be associated with the spring constant. Let me just, that's in my head right now. Let me see if I can figure that out. Um, that's weird. Never thought about that. Yeah. Hmm. And you won't have any relationship like this because that constant. Yeah, that's interesting. Well, yeah, sure. So, just I digress. So this is actually what I meant to say. The relationship between E and the potential energy, and therefore the relationship between E and the voltage. Since we have the relationship between E, potential energy, and voltage as being, the potential energy is equal to or the voltage is equal to the potential energy divided by the charge. And that's three equal signs, meaning a definition. So yeah. So that's it. That's the introduction of potential. That's like what I would be my first second, and they will show those equations there. So they kind of start off with this. That's what I was saying, that they kind of start off by looking at potential from the point of view of force, and field, and I don't know. I come at it from a different point of view, but everything that I've shown you in this introduction is in that first section. Actually, probably a little bit more than what they do. They talk about some of the things I said a little bit later on in the chapter, I think. But these two things, I believe, are what they kind of start that section with, if I was correct. And I've shown you how to get to them. This is just a pure definition, but then we, look at these other things. Yeah, so that's basically the electric potential defined in general, and then we use the analogy of a mass in an external field to define potential energy of the electric potential energy and all those things that we did. So. Uh, hey, uh, how's it going, man? Good to see you. Thanks for this. I think I need to place a work order. My actually, let me turn this off. My tub, I think, is starting to clog. Now, it's been doing it for quite a while, but I always like get some Drano and stuff and put in it, and it kind of opens it up. And it hasn't really clogged up, but it's starting to get to where the Drano is not working. So I think it needs to have one of those. I don't know what you call those things when you put down. Yeah. So I'll put a work order. I'm about to go on break when this class is over. And yeah, but I just wanted to let you know. Yeah. Okay. Okay. Thank you, Claudia. Appreciate it. Yeah. Have a good one. Yeah. Sorry about that. Too much information. But one of the apartment managers came by and put a notice in my door for some stuff. So I just wanted to take an opportunity to grab him, give him a heads up on that. Excuse me. We got 30 minutes left. Well, yeah. So that's the introduction to this chapter. I'll go ahead and open up the chapter and assign the homework so you can start reading through and working through the homework stuff. I guess the next section is to basically do everything I just did with a particle in a constant field, but to do that in a field that's not constant, right? What is the electric potential for a point charge? What is the energy of another charge in the vicinity of a point charge, a test charge, and what does that potential energy look like? Yeah, yeah. I'll check the book to make sure that's where they go next, but I'm pretty sure that's what most books do. So all the things so basically everything that I did just now, I related it to a mass and a constant gravitational field. So the field was constant, and yeah. And so we did all this stuff. But now what I'm going to do is go back, excuse me, and let's think about what the field of a point charge looks like. We know what it looks like. It's kq over r squared. But what if that is the field that's the object that's setting up the field? In the case before, it was a capacitor plate that set up the constant field. In this case, if we have a point charge, right, we know that its field does this. It's radial. That field clearly is not constant, right? That field E is K And let's call this thing big Q. So big Q over R squared. All right, well, what if we have a test charge, a small test charge, let's make it positive, and we bring it in some distance, R, away from the center of my charge. And the terminology that I like to use is the charge that sets up the field. So Q, big Q is that charge, and this guy is my test charge. Now remember what the properties of a test charge: positive and extremely small, meaning it's so small that it's not affecting the field or anything in the vicinity. So it's basically, it's kind of like when we think about like a mass. Technically speaking, this thing has its own gravitational field. And so when we get close to that mass, the field is really distorted. It shouldn't be constant anymore because the field around the area is going to be around this mass is going to be a combination of the field of the mass plus the field of gravity. So, and the field of this thing is actually radial. It looks like this, actually, technically. So when you do a superposition at any point with that radial field compared to the field of the Earth, which is technically radial, but you're so close to the Earth it seems straight down. Well, when you superpose those things, at every point, it's not going to be constant. It's going to be something else. But if you assume that this field is so small that it's being overpowered by the external field of the Earth, which basically it is, then you can just assume that this thing doesn't have any field at all, really, negligible field, and that the field of the Earth is the only thing that matters, and so the field is constant. So we're doing the same thing here. This guy has his own field, but it's so small that really the field of the large test charge Q is the thing that's the only thing that matters to deal with. Yeah. So I'm going to erase the board, take a little break, and then we'll come back and start working on that. We won't finish this today, but I guess I could, I could do a lot of things. I could show about, I guess I do all those things here. First of all, we take a look at the electric potential energy of this, what the electric potential energy looks like now for this charge close to this guy. And then we look at the work done in different ways, what type of work is done, and then radially, and then lateral, and work required to move charge along a radial path, and the present in the field of the charge is non-zero. Combined path, the work depends on it, Yes, so we'll do that first, and then we'll go into potential. And you can get a potential for the control. And then we'll look at some other distributions for potential. So let's consider this. Let me just take a look at your book and see what they do in this one. Get the bearings straight a little bit. So again, this first section here, electric potential surfaces, equipotential surfaces, they said a little bit. I'll talk about that. But the point is, this thing right here is what I just derived. That this equation here is equation 22 here. So they start with that, and then they say for a constant field, uniform field, it's the equation 21. Where was I? Yeah, I've erased it. I said ED, they say EY, E delta X, but E delta Y. So, yeah, doesn't look like they talk about the potential energy or anything in that section, which is, I don't, I like to, they just start off straight with potential, and they don't really say anything about energy. They start in a little bit with work, but they're not explicit. I don't know. That's just a different way of presenting material. I think my way is, I like my way better because I start with something that you know. And here it looks like you don't know any of this stuff. They're just looking at it from such a different perspective that it like just feels all new. And I just they go to potential due to a point particle. So again, you can read through that. When do they finally talk about energy? Let's look over here. Potential charge, potential to electric dipole, potential continuous charge, recalibrate field of potential, electric potential energy. So they kind of do just the opposite. They present all these things with potential, and then they talk about the relationship between potential and energy in the end. I think it's really kind of weird to really charge that, but it's how it's been resonant. The book is like a gazillion years old, and so they do it, but they don't change. Most books I don't think present it like this anymore. Because ultimately what you're going to see is, as I showed you, is that the definition of potential is defined. That's the three equal sign. So potential is defined in terms of energy. So the fact that they would give the equations for potential for these different systems, but not actually define the ultimate definition till after that is a little bit weird to me. I like to define it initially and then do all those things that they do, as subsequently. So basically, probably the only difference in the way I'm doing it and the way they're doing it is if you take this section 24/7 and put it as 24/1, that's probably what you're going to find. And then, of course, I do finish up with looking at, I told you I would. Last chapter, we talked about the field in terms of a conductor. Here, we're going to talk about the potential associated with an isolated conductor. So basically, my notes take 24.7 and put it as 24.1, and then everything would kind of make sense. So maybe you should go read that first. I don't know if you want to stay consistent with my notes, or you could just, immerse yourself in their point of view of how they present it, because it's a slightly different perspective, and that's always nice to have a couple of different perspectives. Okay, yeah. So as noted, I'm going to start off. So we're going to look at a point charge now, but they go directly into the potential of a point charge. What I'm going to do is talk about the potential energy of a point charge, and then use that to define, and use that and this definition, this general definition here, to then write down the formula for the electric potential of a point charge. And remember, the difference is electrical potential energy is energy. It's joules, right? As you use the joules, it's energy. Electric potential is essentially energy per unit charge. So it's joules per coulomb. So that's the main fundamental difference. All right. All right. Okay, again, making the analogy of presentation, I started this chapter by, again, the analogy between gravity and electrostatics, constant gravitational field with G close to the Earth, constant gravitational field with the capacitor plate, direct analogies all across the board. I could do the same thing here. Now, I'm not going to do that as explicitly because you probably don't remember the gravitational potential energy for universal law of gravity, but just to show you that the analogies are still the same. If I were to look at the Earth from a satellite, the Earth's gravitational force looks just like that. But remember, it's not really the force that gives a field. It's the field is in the G part of it. So I guess technically you could define a force field. I said that wasn't earlier, but it really is just defined in terms of G, right? Because the force gets its vector nature from G. And you don't, it really is incorrect. It is incorrect. I'm just go back to that. You could kind of maybe, like I said, there's no force field around the Earth. That's not true. Because there has to be something there for it to be forced upon. Like right now, you say, well, there's a force field around it. Well, that means there's a force field right here in front of my face. Well, I would ask you, okay, what is being forced on? If you assume a vacuum, there's nothing there. So there's no force field there. If you put an object there, now there's a force on that object. But where did that force come from? Well, the force is equal to M times G. The M is there because the mass is there. But where's the G come from? Well, the G was already there. The G is the field. So that's why I kind of make a distinction in the last semester. When we come into mechanics, we just use the term gravity, and you start to hear students use gravity interchangeably between gravitational force and gravitational acceleration. But you have to distinguish. You can't just say gravity anymore, now that now that you're in a physics class. So I force people to say, don't just say gravity, because I don't know what you're talking about. I mean, I could figure it out in the context, but a lot of times the students aren't saying it in the context. Because they're not making the distinction. So I teach that you either say force of gravity or acceleration due to gravity. You just don't say gravity, right? Because force and gravity are not the same thing. They're apples and oranges. One is a force, one is a field. Right? So this idea of a force field, there's no such thing as a force field. There's a field and then there's a force, right? So really what it is just a field around something. And when something enters that, even in these science fiction movies, they say put up our force field. So you put up a field and then they shoot lasers and stuff like that, and the lasers bounce off. What I'm trying to tell you is that there was no force around that object. It can't be a force that they're putting up. There's no such thing. What they're doing is putting up some sort of field such that whatever weaponry, whether it's a laser, is sensitive to that in some way. So in that same way, when that laser beam comes in the vicinity of that field, then the field can apply a force to that laser beam and keep it out or whatever. In the same way, right now, there is no force in front of my face. But if I take this mass and put it in front of my face, now there's a force on this mass in front of my face because the field is applying a force to that mass. And that field was the thing that was in front of my face before I put the mass there. So really, it's technically incorrect to say force field. It is incorrect. It is correct to say field, and then to say that, there's a force, on an object when it enters that field, specific to the physics that dictates the relationship between the object and the field. Just a little bit of a pet peeve, can you tell? Oh yeah. So I was talking about the Earth. So the thing that's actually around the Earth is not a force field. It looks like this, but it is a gravitational acceleration field. And you might say, well, there's nothing accelerating. So how can you say? Because Again, it's just a flipping concept. The acceleration was never something associated with the object, even though that's what we implied last semester. It never was. It is when you're talking about a contact force. It always is. But when you're talking about like a non-conservative force, if there's a ball and you hit the ball, then the force is accelerating that ball in that very small amount of time in which it's on the object. So I guess there's no field associated with contact. So in that instance, it's accelerating, right? But then the ball now is in free fall. And yeah, it is accelerating, but the acceleration is really the fact that it's in, and again, it's really just a shift in perspective, right? But these things are real because it's why perspective is a theme, because perspective is much more than we realize, actually, when we're using it in lay terms. Perspective is everything. It's your reality, right? And we're beginning to have conversations where we understand that as quantum mechanics creeps into popular culture and a lot of these movies. Relativity, right? Depends on the relative nature of where you are, right? We talked about that a little bit with relative velocity. We got into that a little bit, but perspective is really huge. So is acceleration associated with the object or is it associated with the field? I look like some sort of rapper doing, from the 80s. But well, it depends on the type of force you're talking about, is what I'm getting at. If it's a contact force, yeah, you might say that it's something specifically associated with the object and nothing else. But but with a non-contact or conservative force, the acceleration field is there whether or not an object is there or not. And if an object happens to come in that area, it is required to respond to take on the properties of that field. And one of them is that it has acceleration specific to that environment. That's one way to think about acceleration. It's an expanded view. Remember, physics is like an onion, right? So don't let this throw you. Just shift your perspective and then at least appreciate the point of view. You learn something, then you relax criteria and you say, oh, well, that's just a smaller aspect of something bigger, and then bigger, and then bigger, or deeper, however you want to think about the analogy. But the whole universe is like that. So you just have to get used to that. You learn something, you get comfortable with it, then you scan out a different perspective or multiple dimensionalities, however you want to define perspective, and you see the thing that you thought was so precise and specific is just a smaller case of a larger, more universal concept. So that idea of always changing, you have to get used to that in science and certainly in physics. So you thought you understood acceleration. You did from a limited perspective. Now I'm giving you a different perspective. Acceleration is a field. And it is the thing that's actually around the Earth, not force. It's a G field that surrounds the Earth. It's negative, so it points in, right? Unlike the positive charge, which points out. But if I had a negative charge here, the negative charge would point in. Just like we place a negative sign on universal law of gravity, then Coulomb's law would have a negative force for any charge entering that facility. Right. I like to use positive, but whatever. I could have used negative, and it would be directly analogous to the Earth. Again, this is Earth. So I guess what I'm trying to tell you is that the argument that I'm going to make, like if you had someone who comprehensively went over a universal law of gravity, they would have actually covered this. I don't think in the last summer I did that. For those of you who might have had me in the summer, I think I ran out of time. I did cover universal law of gravity, but I didn't get to defining potential. But I'll do it now. I'll do it right, and then you can go back and it's the same. So there's an argument that we have for this. But again, first I'm going to talk about potential energy. And I might have done it really quickly. I don't know, but I didn't really talk extensively about it because I didn't go. Yeah. So what happens if I have a test mass in the vicinity of this gravitational field? You see its direct analogy here. So the argument that we make is I'll set this up, and then this is where I'll start on Wednesday because I'm gonna run out of time. I like it. Well, actually, I might go a little bit over because I didn't actually start the lecture until maybe 15 minutes in. So I might go another 25 minutes or so as opposed to finishing in basically 7 minutes. And that might give me enough time. My head is cold. Sorry, I'm just putting my hat. It's kind of funky, so I have to keep it real chilly. Oh. So remember that the universal law, like this G field here, G is analogous to Coulomb's law, right? G is equal to G, the universal law of gravity. And let's call this big M. So this is the mass of the Earth is, I'll just, because it could be any planet, I'll call it a capital M. So it's going to be capital M basically over R squared, R hat. Clearly has the same functional form as this guy, okay? So everything, I'm going to now switch back over here, but everything I do over here in everything that I described, ultimately, I'm going to make an argument, a qualitative argument to describe what electrical potential energy is. Then, as I said, I'm going to use that description to then define electric potential for a point charge for a 1/r squared distribution, which is not a constant field like it was with the capacitor. Everything that I say, you just come over here, you replace a Q with an M, and you're going to get the analogous results. So the analogy does indeed continue, even with non-constant fields, but we just didn't go over it as much or as explicitly with gravity last semester because for a lot of reasons, we're at the end of the chapter and at the end of the semester usually, so we don't spend as much time. So I'm gonna, you can go back and do what I do over here and just derive the equations for yourself, and see. And I might write them down afterwards, but just see how you get those. Everything I say is exactly the same. It's just replace the charge with the mass, even the qualitative description stuff. Okay. All right, so let's switch back to this semester and what we're doing now. The first thing that I want to ask you, I want you to think about this. We're talking about potential energy. Remember, energy is energy of position. When we do it in a constant field, it's very easy to define a zero potential energy point, as I have talked about earlier, last semester, and a little bit I alluded to it earlier today. Where is that point? Well, we can put it wherever we want, but usually if we're close to the Earth, assuming the Earth is flat, I'm not a flat earther, I'm saying that very close, it seems flat. It seems like the flat earthers are, you know, I'm sorry. I try to make a point of not laughing at points of view that are very different from my point of view. Just a quick side note. Oftentimes I found in life, and certainly in physics has taught me this, that no matter how crazy something sounds, there can be some sort of truth in it, right? If you have two different positions, sometimes, most times, the truth is somewhere in between, not necessarily in the middle. It can lean toward one or the other, but there's usually some aspect of both points of view that are actually true. And if you don't understand that, if you're so solid in thinking one or the other, then that can be exploited through fear or whatever. So I apologize, for laughing in that way, because it's not that I think these things are completely ridiculous. I just think that oftentimes things can be really counterintuitive. And that's the nature of physics, is what whole physics is right, because you need to investigate things. Two things that seemingly could be true, maybe they are, maybe they aren't, maybe they're like different aspects of the same thing or whatever. So, yeah, I'll just leave it at that. Back to this. Um, I was talking about a zero potential energy point, and so, relatively speaking, close to the Earth, we make the assumption that the Earth is flat, and so therefore, it's a very nice place to make a zero potential energy point when you're only considering things. Your universe is just the Earth. But when you really think about the universe as the universe, and you scroll out 80 miles or 100 miles and see that not only is the Earth spherical, but you look around in the universe and everything else that you can see around you is spherical. And now, when your mental playground becomes literally the actual universe, or at least our galaxy or whatever, the universe, as opposed to just being on the Earth and considering only things relative to the surface of the Earth. Now, when you scan out, the surface of the Earth, first of all, it's not flat, it's round. And secondly, that's just one of a gazillion billion other things that have gravitational fields. And if you really want to, so my point is, where is the most logical place that you would choose to be your zero potential energy point? That's what I'm getting to. It's not so obvious when you're floating out in space and you're trying to do a problem like this, because you got to measure it against something. Do you put it on the sun? Because the sun is the center of our galaxy. Well, that might be reasonable. It might be reasonable if you're just thinking about our galaxy. I mean, our solar system, excuse me. Well, what about, there's Andromeda is the nearest galaxy. So now if you scan out even further and you look around, the universe looks exactly the same. But whereas when you were in our solar system looking around, everything was stars and galaxies. Now, when you scroll out a couple, whatever, gazillion, well, maybe 10 to the 6 light years, and you're literally out of the solar system, but in the galaxy, you look around, it looks kind of the same, but as opposed to everything being stars, they're all galaxies, right? My point is, and they all have like, where is the zero potential? Like, it doesn't make sense then to put the zero potential point on the sun, because that's not the biggest thing. Well, you maybe go to some big galaxy, and I don't know, like where? Like, you're looking around, you're floating around. I got to do this problem. I need a zero potential energy point. Well, when you're on the Earth, it becomes obvious because of the functional form of the potential energy, that no matter what mass an object is, when it's on ground at zero, because you have mg times the variable that defines the position away from the surface, whatever object you have, that variable is zero. So my point is that no matter how big the object is, when it's on the surface of the Earth, if you define that as the zero position point, then that's also got to be the zero potential energy point for any object. That's why it's a natural place, not just because the Earth is flat. Any place I had to find the zero potential energy point, the energy would have been zero. It just so happens that the surface of the Earth is the most convenient place to do that, because I'm standing on the surface of the Earth. But it's not because somehow the surface of the Earth is an inherent zero potential energy point. It's only that because I placed my origin there and made it zero. And that's the most convenient place for me to do that.
because that's where I do everything else from. You're measuring things from a reference point. I mean, I could put the thing on the top of the Empire State Building, but why? Why would we do that? Right? That's not really a common reference point for people in Chicago. But everywhere on the earth, a common reference point for people is the surface of the earth. Starting to get it now? You understand what I'm saying? That's why we do it. So now, again, we're out in space and we're intergalactic travelers, and we want to work a problem, a simple problem, but we gotta, like this kind of thing. But basically, we want to calculate this, the potential energy of this thing, close to maybe my ship, close to a planet, whatever, a galaxy. But I got to calculate. So I got what? Where's the zero potential energy point? Well, if in class, I'll be calling you to ask you to guess. But it's got to be a place where no matter how big the object is, what the properties of the object, it doesn't matter, that when I take all objects to this point, the potential energy is zero in this electric field, this non-constant electric field, in the same way that close to the surface of the Earth or any planet, the zero potential energy point, the most common and sensible, would be placing the axis on the surface of that planet there. So where would that point be if I'm out in space someplace? And there is a point, there is an answer. Where would it be? Well, intuitively, you might think, well, we know that the force is attractive between like charges or unlike charges and repulsive between like charges. So as I bring this charge closer, this test charge closer to this charge Q, there's a force on that charge that's pushing the thing away. And that force gets larger as I get close, as R gets smaller, right? Now, we haven't quantified it yet. We will. Well, we did. We know it's a Coulomb force. Well, you don't have to think about quantitative. Just think qualitative. We know what the properties are. So there's a force on this guy that's pointing in that direction. It's Fe associated with this charge is forcing on that charge. Yeah, you could say the field is doing it, but we know the field is coming from the charge, blah, 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 right? And you intuitively know, as I said, third time I'm saying that as I bring this charge closer, this force gets larger. So what does your sensibility tell you? So the corollary to that, or converse of that, is that if I take this positive charge and take it farther away, increasing R, then this force should get smaller. And I haven't even quantified. I haven't talked about how much charge that is, whatever. Well, I said I did. It's a test charge. But for any charge, whether it's a big charge that's not a test charge, whatever, that will be true, qualitatively true. That if it's positive, as I move closer, the force is larger, pushing it away, repulsive, and then farther away, the magnitude of the force decreases. Even if it were a negative charge, now the sign flips, but the magnitude, the thing is the same. Like if I bring this negative charge closer, the attractive force is stronger. If I move away, the attractive force is smaller, right? So the magnitude of the force, whether it's positive or negative, behaves the same way. The closer I get to the charge setting up the field, the stronger the force. The farther away I am from the charge setting up the field, the smaller the force. So with that qualitative understanding in mind, where does your intuition tell you is the place in the universe where that force will be zero? There's only one place, and it will be the same no matter what the magnitude of the charge. Actually, and again, they're the same thing for gravity. I could just come over here. There's a gravitational force attractive on this in that direction, right? It's always attractive. You don't have to flip back and forth based on a sign or whatever. Where does that force, where's the magnitude of that force? Zero. Strong when I get closer, we're going to get away. Where's the place? There's only one place. Well, if you said infinity, then you would be correct. The Coulomb force of large Q on test charge Q is only going to be zero whenever test charge Q is on the infinity wall. The infinity wall. Let me make the infinity wall over here so you can see it. That's F. And the infinity wall, W-A-L-L, is this guy. That is infinity right there. When my charge gets over there, it's so far away that F actually goes to 0. Same thing here for gravity. Now, when my charge is on that wall, it does not have an attraction. The attraction of the Coulomb force, this guy is 0. So it doesn't have a force on it, nor does it have energy associated with it. When I am setting up a system, where does the energy come from? The potential energy come from between a charge, test charge Q, that's a distance r away from some charge setting up the field. It comes from, I don't know, a universal, and again, we don't have to get into this conversation, whether you want to think of it as some universal being or we don't know. However, whatever call, I mean, one, and I'm not saying that this happened, I'm just saying that this is a mathematical construct to define where the energy is coming from. Whether someone did it or it just happened, I don't know, but, or some intelligent design, you have to, the argument is that you, and I'm not saying, again, that this literally happened, I'm just saying that this is a kind of an argument to describe how the energy is and where it comes from in the system once you bring two masses or two charges in close proximity, like electrons around the nucleus, and there is energy in that. Actually, that's a good analogy. Like, but this is a positive charge, so if we're a negative charge, I could say something like whatever. These are in this specific case, this is a repulsive force. As soon as I pluck this thing off of infinity and bring it a distance less than infinity, a Coulomb force appears on this object. It's very infinitesimally small, but it's there. And it starts to increase as I bring the test charge closer to charge Q. Okay, well, that is analogous to me picking this mass off the ground, right? Like, same thing. It's like the force is opposite direct. The gravitational force is down. So once I bring it, I'm picking it up. Well, I guess it's attractive, but anyway, you know, like I'm doing work on it to pick it up because there's a force that naturally wants to keep it on the ground. Well, similar thing here. The repulsive force of Q setting up the field wants to keep this charge on infinity because it's a repulsive force. So as soon as I come in, pluck it off, and start to move it toward this charge, I'm doing work. I'm working against the field here, just like I'm working against the field of gravity as I pick this up. And just in the same way, when I pick it up to a distance h and leave it there, that work that I did has now gone into this object as potential energy of position. Direct analogy here. I can pluck this thing off infinity, do work by bringing it all the way in, all this distance, and then putting it some measurable distance r away from this charge. Well, I had to do work on the object to do that. And now that work has gone into the system now being the two charges, right? In this case, the system was actually it was the box and the earth, but we didn't look at it from that point of view back then. We just said it was the box and I guess the field. But really, here we have the two test charges. So the work that I have done in order to pluck this thing off infinity and bring it a distance r from the charge setting up the field, that work now goes into the system being the combination of the charges and their relative distance. That work is now the potential energy, the electric potential energy inherent within that system. Let that sink in for a little bit. And I can figure out how much potential energy that is by doing the exact same thing I did to calculate the potential energy of picking that box up in a gravitational field. And remember, what was that I did? I picked the box up at a constant velocity so that the force that I was using to apply was equal and opposite to the force of gravity that was pulling it down. And then I put that force in the work function, work equals F dot dx, and I calculate the energy. And then I defined that energy, or that I calculated the work, and then I defined that work as the potential energy of that system. I can do the same thing here. The same thing here. Now, I'm going to pluck this thing off as I did, and I'm going to move it in at a constant velocity along a straight radial line toward this charge. If I want to calculate how much work that is, then this is the problem that I have to work out. And I'm gonna set this up. Then I'm gonna stop class here because now it's I'm going giving you your time back that you paid for. But this is in the book, and this will be like, you can skip the chapter. I would skip to section 7 because I think it's important to do this before doing all the others. I don't know why they put it at the back of the chapter. I have no idea. I don't know. It's just a matter of whatever. Whatever. So this is the thing. So the work is going to be equal to the integral. Now remember, I'm going from infinity to this position r of f dot dr. Dr is the real line. Now remember, one stipulation is why I always say that, is that you have to do it at a constant velocity to be specifically correct, because if you do it at a constant velocity, technically this is not Coulomb's law. This is an applied force. But if I'm bringing it in at a constant speed, a constant velocity, not changing the direction either. So calculate the work, calculate the work done by an applied force to applied force F5 to bring an object in to position R from infinity. Then define that amount of work as the potential energy for that thing. Well, if I bring it in, then Newton's first law, we see that the applied force is going to be equal to the Coulomb force, because the Coulomb force is the thing that's retarding the motion right here. Here's the applied force, F applied, and the Coulomb force is the thing that's trying to push it away as I bring it in. So no acceleration at equal and opposite. So I'll call this equation 1, this equation 2. What does the Coulomb force look like? Well, equation 3, the Coulomb force is going to be equal to Q, and let's say that this is small q, right? S charge Q, Q plus, and we make this Q, large Q plus. So the Coulomb force is going to be K E, large Q plus, small Q plus, over R squared in general, wherever that is. So now in this case, I'm doing positive, well, dr is always defined as pointing out, and F is applied as in. So in this case, I guess I'll go ahead and do the problem for you. Well, I'll set it up, let you do it. So then FE is equal to, if I stick that in, the work is equal to integral to R, I'll make it a definite integral. And I have F basically, now remember, the magnitude is FE, so that's in the same direction, but it's F applied. So I guess F applied dr cosine of 180. Now, if it were a negative charge, there would be, I would have to be, my force would be, if I do it at a constant velocity, my force, I'd have to be holding it back. So Fe would be in, and F applied would be in the opposite direction. So either way, you're going to generate a negative sign, no matter which one you do. That generates -1. So then I have work is equal to integral infinite R. So negative sign I put out there, and then I have F applied dr, but then F applied is equal to Fe. So the integral that I'm working out is a negative integral from infinity to R of, well, when I put it in, I'll take all the constant stuff out. I'm going to have, well, I'll do it in 2 steps. So integral of infinity to R of Q plus over R squared dr, and that's actually the case of B is there. I was going to let you do it. I'm doing the whole thing now. Cleaning it up, the work then is equal to negative K sub B. Take out the Q plus, integral of dr over R squared. And that's a simple integral that you can do. You're going to end up getting its integral, right? So with integration, it is of the form integral of x to the n dx is equal to 1 over n plus, no, what is it? Oh, yeah, 1 over n, 1 over n x to the n minus 1 plus a constant, or an indefinite integral. But this is a definite integral. So this is going from infinity to R, so we won't have to worry about the constant. Oh, God. Yeah. Now let me show you where this is in the book. Before, I think I showed you, but we didn't go inside that section. It should be in here. They should do all this and talk about all this here. So electric potential energy, yeah. There you go. Let's jump down to this. And here yeah. So they're going to get that result. We're about to get that in a second. And yeah. Here they're talking about what I just said. So that's how they present it. And they don't derive it. They just write the answer down. That's kind of BS. That's a cop out. Doesn't look like they derive it. Not really. That's a bit of a cop out. So they don't do what I'm doing here. That's a bit of a cop out. Okay, well, maybe they do it someplace else in the book, and I don't know. Yeah, I don't know. That's a cop out. So at least you're seeing it. Well, what's the integral of this thing? Remember, this is like r to the negative 2. So actually, no, it's negative. It's n minus 1. That I'm sorry. Wow, folks, I'm sorry. I'm like getting really, I need to go back and review all my little calculus stuff. It's going to be integral of x to the n dx is equal to 1 over n minus 1 quantity times x to the n minus 1 plus c. Sorry about that. Whew. Rusty. So let me show you where they get that equation from. It's just doing this integral. So now I've got the work then is equal to minus k of e q plus q plus, but then I've got the integral basically of r to the minus 2 dr. So if I just apply this formula, do the integral. Oh, sorry, this is the plus 1. You do integral, right? Yeah, integral is plus 1, derivative is minus 1. Wow. So yeah, sorry. So r to the negative 2 plus 1 is negative 1. So then I'm going to have, man, I'm getting rusty. K sub b q plus q plus. So this is going to be, so minus 2, minus 2 plus 1 is basically 1 over minus 1, which is so now keep in mind there's a minus sign that's already there. So I'm going to put the derivative in the integral in parentheses, and then we'll work out the algebra. So minus, that's this thing. The minus 1 is this quantity, and then times r to the n plus 1. So minus 2 plus 1 is minus 1. And that's it. The minus here cancels the minus here. R to the minus 1 is 1 over r, and that's the answer that they got. That the work is equal to k sub b, remember k sub b is 1 over 4 pi epsilon naught, times q plus over r. And that's the work done. That is the work that is required for me to take a charge from infinity and bring it in a distance r from a point charge that's setting up a Coulomb field around itself. Again, just to make sure you believe me, let's go back and look at that result again, and you'll see that that's what they did, or that's the answer. They didn't do it. They just wrote. I don't know how they. Did you see? That's it. Oh well, they jump right to the potential. I want to do that in a minute. But the energy, they say it here, the change in potential, they don't work it out, but that's the change in potential energy. Well, actually, that's the work done. They didn't even do that. Well, they do it here. That's where they do it up here. I don't know where they describe, but that's how you calculate the work. Now, we've already said that the work is equal to the negative of the change in potential energy. They're using absolute values there, and we can do the same, but yeah, that's it. So yeah, because you can say that the work is equal to the negative. the general definition of potential energy is that work is equal to the negative of the change in potential energy. Then what they're doing is just taking the absolute value, because you see that the functional form has to be the same. So just taking the absolute value, I can define electrical potential energy for a system of point charges, just take the absolute value. And so that's how they get it. And define the potential energy of a point charge, UE, of a point charge is equal to basically. And so again, we're using the definition of potential. So, well, the potential energy, sorry, E, is equal to basically K sub B, Q plus over R. That's the definition coming directly from equating it to work, right? And then the next thing they do is define the electric potential for a point charge. And now that we have the definition, the general definition of electric potential, that electric potential delta V is equal to delta U over Q. Now remember, this is the Q that we're talking about the energy of. So in this case, it would be the small q. That's the thing that has the potential energy, and therefore, well, actually, it's not really true. It's kind of a really we kind of shifted our perspective here when we said that the gravitational potential energy was just the energy of the object. That was actually never true. It was the energy of both the object and the Earth. But we kind of made the Earth. We didn't really consider it. We were just considering the field, the G field that came from the Earth. We could do the same thing here, but generally what's done is we think of it just the system now, because we're kind of so far back that we can see where the field is coming from. It's coming from this charge. So what we really say is that the system is both. So when we describe the potential energy, really we say it as it's the potential energy of the system, which includes both charges. But we still define the potential energy in terms of the test charge. And so then when we equate these two, if I take this guy and put it in here, then basically the Q's will cancel out, right? I basically think of it like this, 1 over Q plus times delta U. So obviously when I put this in, the Q's will cancel out, and I get that delta V is equal to K sub B Q, the charge setting of the field, over R. And finally, if I think of this delta V as V at R, because it's final minus initial, so the final is the potential at this point, and the initial was the potential at infinity, equals K sub B Q plus over R. Well, in the same way I define the electric potential energy as 0 at infinity, then the electric potential is also defined to be 0 at infinity. And so that's where they get this formula that the electric potential of a point charge, V of R, is equal to K sub B Q over R. And it's not a vector, it's a scalar, right? Potential is a scalar because you get that directly from the definition. Charge is a scalar, energy is a scalar, so potential is a scalar. I didn't say that before. I told you that it has units of joules per Coulomb, but you can infer from that it would be a scalar. In fact, it is. So there you go. That's section 7, basically. So that's what we have. We have the work done to bring a charge in from infinity. We have the potential energy of the system once that's done. And we can then define the potential energy, the electric potential in a region surrounding space. Now, it's more we'll talk about with this, but one thing I want to show you is that this value, that is the potential at that point where the charge is, whether that charge is there or not. It's kind of like talking about the field, right? The field is there, whether that charge is there or not. E is there. So the potential actually is there as well. And yeah, so I'll start there on Monday, and I'm going to switch back up to section 1, because this is where I like to talk about equipotential surfaces and equipotential energy surfaces. If you notice in section 1 of the book, they start right off talking about that, which is fine. But I have a certain way that I organize the material, and this is how I do it. So I'll start off by talking about, in this case, it would be equipotential spherical surfaces every place a distance r away from the center of that charge distribution will have the same electric potential. And if I have a charge, you know, and I, at everywhere on a spherical distance r away from that, it would also have the same electrical potential energy. Just in the same way, if I took a mass and picked it up a height h, I could talk about equipotential plane, where no matter where I am horizontally, if I'm vertically the same distance away from the zero potential energy point, namely the ground, then the potential energy of that object is the same everywhere. So we can define an equipotential plane. And ultimately that mimics the geometry of the surface of the quantity, the object that is setting up the field. So we'll start there on Wednesday. Okay, I'm gonna go ahead and